The human excretory system operates as a meticulously organized, high-pressure purification engine. To understand how it functions, we must look at its anchoring. The kidneys are located dorsally, positioned at the back of the abdominal cavity, locked firmly between the level of the last thoracic vertebra, T12, and the third lumbar vertebra, L3. Notice their alignment. They are structurally asymmetrical. The right kidney sits slightly lower than the left, pushed down by the massive weight and footprint of the liver positioned directly above it. Their specific placement is classified as retroperitoneal. This means the kidneys are situated entirely behind the peritoneum, the membrane lining the abdominal cavity, which only covers their ventral or front-facing side. Looking closely at the physical parameters in this diagram, an adult human kidney measures roughly 10 to 12 centimeters in length, 5 to 7 centimeters in width, and 2 to 3 centimeters in thickness. The average weight sits between 120 and 170 grams. This exact dorsal pocket, the asymmetric mounting, and the compact density are structural prerequisites. This organ must physically withstand processing the entire blood volume of the human body repeatedly throughout the day. To survive that continuous internal pressure, the organ requires a primary defense layer. It is tightly enclosed by the renal capsule, a tough, fibrous outer covering that protects the delicate structures within. This diagram highlights the inner concave surface of the organ's classic bean shape. Right at the center lies a crucial notch known as the hilum. The hilum acts as a strict bottleneck. It is the exclusive gateway for the organ. The ureter, every incoming and outgoing blood vessel, and all nerves must traverse this exact point. Just past that bottleneck, the internal space opens up into a broad, funnel-shaped cavity called the renal pelvis. Along the outer edges of this pelvis are cup-like projections called calyces. These act as collection funnels for the final liquid output. By restricting all vascular and nervous entry to a single localized point at the hilum, the kidney effectively isolates its high-pressure internal environment from the rest of the abdominal cavity. Slicing the organ longitudinally reveals how the internal tissue is divided into two distinct geographical zones, the pale outer cortex and the darker striated inner medulla. Notice the medulla is not a solid mass. It's segmented into conical structures called medullary pyramids. The narrow tips of these pyramids project directly into the calyces of the renal pelvis, forming a continuous pipeline for waste to exit the tissue. To maintain this arrangement, the outer cortex provides the physical scaffolding. The cortical tissue actually extends inward, wedging itself tightly between each of the medullary pyramids. As detailed in the text here, these specific inward-reaching extensions of the cortex are called the columns of Bertini. This interlocking architecture, where pyramids funnel waste and cortical columns provide structural integrity, creates the exact foundation required to house 1 million microscopic filters. Embedded across these two macrozones are the actual functional units of the kidney, complex tubular structures called nephrons. There are roughly 1 million tightly packed into each kidney. A nephron's individual components are not scattered randomly. Their placement is strictly dictated by the geographic boundaries of the cortex and the medulla. We start in the outer cortex, which houses the Malpighian body, the initial processing head. The highly coiled proximal and distal tubules also reside exclusively here. But the hairpin-shaped loop of Henle dips down, crossing the boundary deep into the medulla. We categorize nephrons based on the depth of this loop. Cortical nephrons have short loops that barely breach the medulla, but a critical minority, the juxtamedullary nephrons, feature immensely long loops that drive deep into the medullary core. This mapping proves the tissue's function. The cortex handles initial high-volume processing, while the medulla drives deep concentration. Looking at this routing diagram reveals a physiological paradox. The blood leaving the liver via the hepatic vein carries the highest concentration of toxic urea in the body. Yet, the blood exiting the kidney via the renal vein is the purest. The static nephron tubule cannot achieve this purification on its own. It requires a tightly integrated parallel vascular network to deliver that impure blood directly to the processing heads. High urea blood enters the kidney from the dorsal aorta through the main renal artery, rapidly branching down until it forms microscopic vessels called afferent arterioles. The critical interface happens here. The afferent arteriole pushes blood into a dense tuft of capillaries, the glomerulus, nested tightly inside the Bowman's capsule. This handwritten note points out the mechanical mismatch that powers the entire organ. The entering afferent arteriole has a significantly wider diameter than the exiting efferent arteriole. It is a matter of fluid dynamics. Forcing a high volume of blood into a wide pipe, but restricting its exit, creates a massive, localized high-pressure zone. This pressure physically squeezes plasma and waste out of the blood and into the tubule. Glomerular filtration doesn't rely on cellular energy. It is a brute force mechanical trick, dictated by the structural asymmetry of these microscopic blood vessels. The concentrated, sludgy blood that survives that high-pressure squeeze exits through the narrow efferent arteriole, but it does not leave the kidney immediately. Instead, the efferent arteriole branches out again. It weaves a secondary web called the peritubular capillaries, wrapping around the PCT and DCT to actively reabsorb essential nutrients that escaped during the initial squeeze. From this network, a specialized capillary extension emerges. The vasa recta is a minute U-shaped vessel that drops parallel alongside the loop of Henle, diving deep down into the medulla. As stated in this text, this deep-diving vasa recta is highly reduced or completely absent in standard cortical nephrons. It exists primarily to serve the deep juxtamedullary nephrons. After shadowing the tubule system, these capillaries finally merge. They consolidate into the renal venule, funneling outward to join the massive renal vein. The excretory system functions because of this strictly mirrored dual journey. A tubule system mapping deep into the medulla, shadowed flawlessly by a vascular network designed to extract waste, reclaim water, and return the body's purest blood back to the heart.